Hello everyone and welcome to another video. So today I'd like to have a discussion on the chain rule. In terms of an agenda, what I'd like to do is just do a quick little introductory problem just to get our feet wet with some derivatives. And then I'd like to look at applying the chain rule to a single input, single output function. This is something that I'm sure you've seen maybe all the way back in high school. There's countless videos, references, examples, tutorials showing how to do this for a very simple single input, single output system. And that's great. I'm not going to spend a ton of time on that. Instead, what I'd like to do is introduce this, build on this concept though, and extend it to something that I don't see a lot of coverage or discussion on, and that is extending this idea of a chain rule out from a single input, single output to something like, what if you had a multi-input, single output system? And in fact, here's where we are going to look at breaking this down into two subtopics. We're going to introduce how you can use a composite function formulation to look at this, which allows us to bring some higher machinery into bear, namely a Jacobian matrix. And we're going to see that that is actually a lot better way to formulate this problem, because then we can extend this multi-input, single output to a multi-input, multi-output, or a generic function. And we can look at how does the chain rule apply in that case. And that's going to be a stepping stone to a lot of more interesting applications down the road. So again, like I said, this first part is something that I think you'll see a lot of other coverage on, but instead I'd like to just lay the foundation of this and actually look at some of this more complicated discussions and see how the chain rule can be applied in higher dimensions. So if that sounds fun, why don't we just go ahead and jump right in. All right, so to set the stage for a chain rule, let's just consider a really simple function here. So I've got some function h. It just is something like this. I don't know, it's 3u plus 4u squared and then that quantity cubed, okay? Anytime I see a function, the thing I immediately like to do is I like to draw this box, right? I like to draw this picture of what is a function. A function, it's just something with inputs. In this case, the inputs are clearly u, and the output is, I don't know, something, let's call it w, right? This function, it takes in a single input, spits out a single output. The way it does this computation is through this, right? So what the chain rule is doing, and it focuses on not looking at just the actual input and output, but really it's looking at the derivatives or the rates of change of the inputs and outputs and how are they related to one another. So what we can do here is, let's forget about chain rule for now. Let's just say, okay, inputs and outputs, or derivatives of the inputs and outputs, right? Just take the derivative of the function, right? You can do that. In fact, right, they taught you how to do this in high school, right? You have this kind of a function. If I want to take its derivative, what I have to do, right, is I have to take the derivative of the outside and then multiply it by the derivative of the inside. So this thing in green, in the green parentheses, you can clearly see all we're doing here is we're taking the derivative of this whole thing. So this 3 comes down, the power becomes 2, and then you just leave the inside alone, right? But then you have to multiply by this thing in red, right? This thing in red is the derivative of just this inside term, right? It's just the derivative of 3u plus 4u squared, right? I take the derivative of that with respect to u, right? So this red thing becomes this down here. So it's just, 3 plus 8u right here. And then we have the thing in green just comes right down. So here you go. This is the derivative of this function with respect to u. This is going to describe, right, how if you have some kind of change in u, right? If this u number moves up or down, right? How does the output move up or down, right? That's what this is measuring, right? So again, nothing fancy, but I do want to just kind of set the stage, level set. This is the answer, right? Can't argue with this. This is how you get the derivative. You can use these, quote unquote, brute force techniques or these rules that we learned earlier, and that's fine, right? But now I want to consider, okay, where did this really come from, right? What's the mechanics of what's going on behind the scenes, okay? So to do that, let's consider breaking this function, this h function, instead of just being a single kind of monster function here, what if I want to consider h to be a composite function, meaning it's composed of a function g and a function f. And what I mean by that is, let's go ahead and expand this, and I can redraw this simple block diagram, this same function, like this, okay? So what happens is u still comes in, right? You can see that's an input. But first, we've got some function, let's call it g, okay? What this g does right, is it just does the inner portion of this function, right? Just this part that maybe, let me be consistent with colors, I'll outline it with green, right? It just does this part, right? It's just 3u plus 4u squared, okay? This function g, it's going to do the inner part, and then it's just going to spit out some other variable x, okay? This x then goes into the outer part, right, which is this, in this case, it's just the cubing operation, right? So that's all this does, and then this function f, which does the cubing, spits out w. So does everyone see how this function in purple is the exact same thing as this function in black? In fact, they're both h. It's just I've decomposed it now into two separate functions, right? So again, we can ask ourselves kind of the same questions, right? We want to understand that if you have a change in u, right? If this u number moves up or down, what is the corresponding movement of w, of the output? That's all a derivative, or all a, yeah, basically that's all the derivative is measuring, right? It's sensitivity of the output to an input, right? So the way you can think about it now with this sort of composite function, right, is, okay, let's go ahead and ask ourselves, what if I vary u, right? So in this case, let's just pick some number. Let's say u is 1/2. I put in 1/2 into this, right? You can turn the crank, go through all this, right? And you can figure out what is the corresponding output w. Really though, what I'm asking is, okay, if I put in 1/2, and now if I vary this by a little bit, if there's some change or some variation in u around this 1/2 number, how much does the output vary, okay? So the way I can think about this is, okay, let's just first look at g, right? Because clearly if I mess around with u, this variable x is going to vary, okay? And I can just focus on this green function first, right? So for example, this green function, 3u plus 4u squared, I've gone ahead and plotted it here. Check the lecture notes if you want to see a better drawing of this. I tried to just sketch this. Again, all these lecture notes, if you check the description of the video, you should find a link to get all of the PDFs for all of these discussions. So download that and look at the better picture. But the idea here is, okay, let's consider that you are at 1/2. I've drawn this point right here. So you can clearly see in this case, right, if I am sitting here at 1/2 and I vary u, I have some delta u around this, I'm going to get a corresponding delta x. And the delta x is related to the delta u through the slope at this point, right? So this derivative of dg du, right? That's this slope right here, and that has something to do with how x changes with respect to u, right? That's all that derivative measures. It's a rise over run, okay? So if I know what the slope of g with respect to u is, this is going to help me in the future, right? Because this is going to tell me how this x changes, okay? Now what I can do is I can do the exact same operation and just focus on the f here, and I can say, okay, now that this x is varying, that variation is going to go through f to produce a variation in w, right? Now where this gets interesting, right, is that we saw that this variation in x, this slope here is not necessarily unity, right? It could be very steep, it could be very shallow, so a perturbation in u could produce a big or a little change in delta x, depending on the slope, right? So I've tried to kind of draw that over here. Like you can see this is kind of bigger than the delta u, but that's all I'm trying to capture, is to say that the slope of both of these functions matter, right? So if I have a variation in delta x, depending on the sensitivity or what the slope of this function f is at the point of interest, that is going to give me a slope here, tangent line right there. And this tangent line is going to be related to the output. So in this case, what I'm looking at is I'm looking at how sensitive is this function to changes in x, right? So again, this is actually kind of interesting to think about, that not only does it matter where you start, right? Because if I put in 1/2 through here, apparently what this x number comes out to be is, you can turn the crank on this, I think it comes out to be 5/2, right? So now 5 halves on the f of x function is over here, and you can see the slope is different. It's steeper here. So overall, the change in the output to the change in the input, you can clearly see you have to multiply these slopes together, right? The slope of g and the slope of f both matter in this calculation, right? Or that's basically what the chain rule states. So this is what you probably saw in high school, right? People said that, okay, if I want the slope of the output with respect to the slope of the input, right, or with respect to a change in the input, right? So dw du is dw dx, right, which is basically this slope, right? df dx is the same thing as basically dw dx, right? It's the change in how this output with respect to this input through the function f, right? So that's this term, this picture, right, times dx du, right? Here's dx du, which is the same thing as dg du, right? So this is where this comes from, right? People always make this note, they say, oh yeah, these dx's cancel with these dx and you end up with dw du. This is just a handy, I think, mnemonic. This is really what's going on behind the scenes, right? You're looking at multiplying the slopes of these two composite or functions that are in series like this, right? So this is what you end up with. And actually, now that we understand the mechanics, we could even be a little bit more explicit about what this is, right? So really, we're talking about the slope of the output with respect, or the output with respect to the input, the changes. This has to be evaluated at a specific location, u, right? In our case, this u was 1/2, right? We said the slope or the answer you're going to get depends on where this number is, right? Because this is going to move you around on this curve, which is then going to move you around on this curve. So really, this is what you end up with, right? It's you have to go ahead and evaluate dw dx at the x location of interest and multiply it with dx du at the u location of interest, okay? So again, let's recap this before we go into the example, right? All we're saying here is the original problem was I want to understand if I perturb or change the input, how sensitive is the output of this function to that change? All the chain rule is saying is that now what you do is, in order to get that answer, you start with a change in u of the input here. What that's going to do is this perturbation is going to actually produce a perturbation in this intermediate variable x right here. The way this happens, right, is it has to go through the function g. So g is going to dictate how does x change with respect to a change in u, right? And now that we have this change in x, we do the same thing and we say, okay, if I understand how this signal x changes, I can then look at how the change in w occurs. And again, we see from this picture that that occurs through the function f, right? That's how you end up with this output. So by chaining or daisy chaining together, this change in u produces a change in x, which produces a change in w. That's all the chain rule is stating, right? So that's it, right? Let's go ahead and now look at our example, right? So if this is what the chain rule is doing, I just need to get these terms, right? I just need to get what is this term and what is this term, right? So let's go ahead and do that. This one over here is probably the easier one to start with. It's dx du evaluated at u, right? So right here, dx du evaluated at u, it's just, where is our x here? Here, okay? So all I have to do is take the derivative of the g function and evaluate it at u, right? So let's just take the derivative of this 3u plus 4u squared, take the derivative with respect to, wait a second, sorry, hold on, whoops, that's a typo. That should be a u. Yeah, dx du, and then I got dw, yeah, sorry, okay, this is now correct. The notes are correct, I just had a little typo here on the board. Okay, so take the derivative of this thing with respect to u, you end up with 3 plus 8u evaluated at u, so this is just stays like this, right? Great, so we got one term. Let's box this guy up. Maybe I'll do it in orange just to be kind of consistent. So we can see that, okay? That's this first term. Now let's get this second term. It's dw dx. So I need to know this slope. How does this w change with respect to that x? It happens through this function f, right? So that's this term right here. I just need to take the derivative of the function f, which is x cubed, with respect to x. So you end up with 3x squared, right? But then you have to evaluate this, right? We know that x here, right? X, it's just 3u plus 4u squared, right? Everyone can see that? Okay, so I now plug in this for x, and you end up with this term, right? And if you look, this is exactly the same thing, right? So here's the 3 plus 8u, that's this thing right here that we got earlier. And then there's this thing here, it's this second term, right? So there you have it. So that's chain rule, right? That's the chain rule for a single input, single output, or you can think about it like a scalar input and a scalar output, right? You put in one u, you get out one w, okay? And again, like I said, this is nothing earth-shattering. You probably have seen this before. Lots of other videos talk about how this works. But now what I want to do is let's go ahead and extend that now to what if this function had multiple inputs and a single output? Okay, so give me a second to erase the board and let's take a look at that. All right, so let's go ahead and extend now this idea to a multi-input single output function. So the example I'd like to look at, let's make something up. Let's say you've got some three-dimensional like rocket engine, and you have a function which is going to describe the temperature in that engine at any given x, y, z location, right? So I made this up. It basically says, okay, you tell me the location x, y, z, these three Cartesian coordinates in the engine. This function will tell you what the temperature is and call that w, right? So again, think about this as now a multi-input, right? 3 input, single output, 1 output function, right? And again, here's a picture that goes along with it. This orange box is maybe like your rocket engine. So you tell me the XYZ location, this function will tell you the temperature, right? Well, if we have this function, we can easily calculate the slope with respect to changes in X, Y, and Z, basically telling you how does the temperature change as you increase or decrease X, right? That's what partial W with respect to X measures. And again, let's just take the partial of this function with respect to X, right? You just get this. Same thing, dw, dy, or I guess we got to say partials now, right? Partial w, partial y, partial w, partial z. Just take the function derivatives, right? Partial derivatives. What these physically mean, right? Partial w, partial x, right? That tells you if you're sitting here at some x, y, z, and you increase x, you move in this direction, how is the temperature going to change, right? Same thing. Partial w, partial y is going to tell you how it's going to change if you move in this direction. And partial w, partial z, it tells you how the temperature is going to change if you come out of the board, right? So none of this is new. This is all, we've seen all this before, right? But I want to get this down. We're actually going to need these later, but let's just start simple, okay? All right, so now let's consider something else. What I want to consider is what happens if instead of Cartesian coordinates, I want to consider describing the position in this engine using polar coordinates, right? Of x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. So again, what that picture looks like now is now we're saying, okay, same point of interest here, but instead of describing it in Cartesian, I want to maybe look at, you have some radius r at some angle theta and some z value. Let's keep the z the same, right? So now what I'm interested is actually, I want to understand how does the temperature change if I change r, theta, or z, right? So what I'm trying to calculate, the goal is I want to calculate how does the temperature change as I change the radius? How does the temperature change as I change theta? How does the temperature change if I change z? So now the picture is, I want now, if I increase the radius, I'm looking for partial w, partial r, right? And as I change the theta at some radius, right, you kind of get this direction, right? This is partial w, partial theta, right? So all I'm doing is a change of coordinates. But what you can see now is that the temperature now It's a function of r, theta, and z, right? So again, we're in this composite function idea where the way I like to think of it is I always draw these block diagrams and lay out what does the function actually look like. So again, I still want temperature coming out, right? That's all I'm doing, okay? I already have this function which tells me how does the temperature vary with x, y, and z. Why don't I go ahead and let's call this function f, right? Okay, that's this function f here. But now x, y, and z, those are actually functions of r, theta, and z. The way these are related is through the polar coordinates, right? So tell you what, let's call this maybe a g1. G1 just tells me what is your x coordinate if you give me the r, theta, and z. And again, that's just right here. Here's g1. Okay, I have another function, g2, which tells me where the y location is if you tell it r, theta, and z. And similarly, oops, sorry, that should be a 2. Lastly, you have a g3, like this, right? It's just simple. This is just a straight pass-through. Z doesn't change in our polar coordinate system, right? But again, the way I now like to think about this is you actually have these three subfunctions. You could think of them as just one function g, which you give it r, theta, and z, it spits out x, y, and z. So 3 inputs go into the green box, 3 outputs come out of the green box, right? And now we can see we're almost in the exact same position we were earlier in the sense that the way you compute the overall output from the overall input is through 2 composite functions. The green box g happens first, then the red box f happens next, okay? So we can see, all right, let's focus on one of these at a time. And I want to go kind of slow. Let's focus on this one. I want to now understand, okay, I've got the entire function laid out. This is the entire function, okay? But now I want to see how does the temperature change if I change r, okay? So all I'm interested in doing is starting over here at r, and I'm actually going to highlight this, okay? I want to now think about varying r. Everything else is going to be constant. I'm going to hold it. All I want to do is I want to change r. So again, this r value is going to go up or down. It's going to be perturbed or vary, okay? I now need to propagate this variation through the entire function to see how does this affect it, okay? So what we have to do is we have to trace every pathway through here from r to the output. So for example, let's start. Let's go up through here. So there's this through here. It's going to come through the function. You know, oops, I'm going to draw it like this and like this. Okay, I tell you what, let's stop right here for now. Okay, I'm going to vary r here. That's going to make its way through here. That variation is going to propagate through this function g1, and it's going to produce a variation in x, right? So this x number is going to go up or down, right? So this first term, right, we can measure this. This is exactly what we did earlier in the single input, single output case, right? This perturbation, this is basically going to be what? It's partial x with respect to r, right? Okay, that's what this first part is, okay? Now, this is going to have to go, this perturbation in x is, again, it's going to cause some perturbation in w, right? How is that going to happen? Well, it's going to come through here, it's going to go through this function, and then finally come out, right? It's going to produce some output, okay? So this blue pathway, we described this first part, but now, how does this change, right? So you can see here, what I need is, I need to understand how does w change with only a change in x, right? I'm going to hold y and z constant for this tiny little bit. Right? So I need to now multiply this with dw dx. Right? So this thing that we've got, this is exactly what we did earlier, right? You multiply these two slopes together. This is telling you how does w change, right, with respect to r, but only through this branch, right? Only through the effect in x. we also have to say that, oh, hey, you know what? This function w, excuse me, the function f, the output also depends on y and z. So let's keep going. So what I mean by that is we haven't traced all the paths through this network, right, or through this function. I got to say, okay, you change r, you're also going to come down. It's also going to change through this function, right? It's going to change y. So you perturb r, this is going to make a variation in y, right? So what is that? Let's write that down, all right? So you have partial of y with respect to r, right? That's this branch. And now this perturbation in y, it's going to change the output w through this function. Oops, sorry, wrong color. I'm trying to be consistent, make all these the same color. I'm trying to use blue for tracing my stuff through. Okay, there we go. So now I've got to go dw dy, right? Because this function, it has a different sensitivity due to y than it does to x, than it does to z, right? Okay, awesome. So I think you get the pattern now. Sorry, excuse me. Okay, so lastly, we got to come down through here. There's one more branch, right? Through here to here, right? Because changing r is now going to also simultaneously change z, right? So you've got now partial z with respect to r, right? And now we finish the branch because this change in z also will come through and change the output w, right? So times partial w with respect to z, right? And now, if you look at this, what we have to do is we have to add all these together, right? So plus, gosh, shoot, I probably should have put them all in the same line. Tell you what, let's rewrite this. Let's move them all in the same line, right? So this plus partial y, partial r, partial w, partial y, plus partial z, partial r, times partial w, partial z. Great. It's like this, right? This here is the total change in w with respect to r, right? Great. So now all we have to do is shop around and get, there's 6 partials we have to calculate, right? So let's go do that right now. All right, so let's go shopping for some of these terms. In fact, we already have 3 of them. All of these sensitivities here, right? How w changes with x, y, and z, right? So that's this one, dw dx, dw dy, dw dz, right? We already got these, right? We did this over here. Check, check, check. 3 of those, right? So all we need now are these other 3, right? We need dx dr, right? And that's right here. So partial x with respect to r, it's basically just take the derivative, whoops, sorry, this should say equals, right? It's partial of r cosine theta, right? With respect to r. And I think you'll see that's pretty easy. What do we get? We just get cosine theta, right? And same thing, partial y with respect to r, it's just take the partial of r sine theta. With respect to r, you just end up with sine theta, right? And then partial z with respect to r, you just take the partial of z with respect to r, which is just a big fat 0. Great, so now we've got the other 3 terms. We need check, check, check. That's x, check, check. So go ahead, you multiply all those things together. And let me see, what do we end up with here? Let's just be explicit. Okay, dx dr, this is just going to be, this first term is going to be r cosine theta. No, sorry. It's just cosine theta. Whoops. It's just that right there, right? It's just cosine theta, right? Times this term right here, dw dx. That was times 4xy, right? Great, so this is this first term, plus, okay, this one, dy dr, that's right here. So this is times sine theta times dw dy, which was times 8y, right? Plus dz dr was a big fat 0 times dw dz, which was 3z squared. Okay? Now, we do the same thing we did earlier, and we remember, hey, wait a second, x, y, and z, x is just r cosine theta. So we're going to have to say, okay, you got to remember that x is just r cosine theta, y is r sine theta, and z just stays itself, right? So you just plug that in for x, y, and z, right? Replace all those, and we finally end up with an expression of how does w change with respect to r, and we have an expression which is all in terms of r, theta, and z, right? Which are these inputs. So I think I just did this in Mathematica to simplify. I think just for completeness, I ended up with 2r times the quantity 3r cosine theta squared minus 4 sine theta, this whole quantity multiplied by sine theta. Great! So there we have it. We got this first term, okay? And now I think you see the pattern. So to do dw, or partial w with respect to theta, right? All you have to do is now do the exact same process, but now instead of tracing the pathways through how r affects things, you trace the pathways how theta affects things, right? So it's going to be kind of hard for me to erase this. Let me see if there's an easier way to do this. Maybe, okay, let's try a different color. Okay, I'm gonna try orange. Okay, so again, orange, what we got to do is now we got to trace how does theta affect everything. So again, you just come through, it's going to go through here, right? And then through this function to come out. And then you're going to have another branch coming through this first function before going through. And then finally, you're going to have another branch coming all the way down through the third function before going through. So those are all the pathways of how theta is going to affect all these other subfunctions before producing an output. So now, just for completeness, tell you what, let's see if we can keep some of these up, because I want to just see how these change and what terms are different. Many of the terms are actually the same. So now, what we're looking for is partial w with respect to theta, okay? So this is now going to be, okay, this first orange branch, right? It's dx d theta, right? So it's partial x with respect to theta. But then we come through here and it's the same. It's saying, okay, now that I have x, how does a change in x affect a change in w? That's still partial w with respect to x, right? Okay, so this term, first term changed, the second term stayed the same. Similarly, you just keep going through this, right? So now we got partial y, partial theta, times partial w, partial y, right? So first term changed, second term stayed the same. Plus partial z, partial theta, times partial w, partial z. Same story, right? So again, you could calculate all these, and again, the only thing that we have to change is this, and this, right? So we got to now modify this term, and this term, right? This partial x, partial theta. So we come back up here, and now I just need partial x, partial theta, right? So I take the partial with respect to theta of r cosine theta, and what do we end up with? This is now r minus r sine theta, right? Minus r sine theta. Hold on, let me just make sure. I'm horrible with mental math. I'm notorious for, like, sometimes I will mess that up. No, that's correct. Okay, good. Then this one, dy d theta, right? So I just got to change this with respect to theta. So now we end up with r cosine theta, right? Yep. And then dz d theta, this is still d theta, so it still is a 0. Okay, great. So again, you know, in the interest of time, I don't want to plug that all in, but it's all in the notes if you want to see what happens. But that's the general idea, right? And then let's do our last one, dw W dz. So again, I do the same thing, trace all the z's, and I don't know, you can see where this is going, right? Let's do this in pink maybe, right? This goes through, z is going to now affect through here, right? And then z is going to come here, it's going to affect through this function, then it's going to affect through this function, right? So that's all the purple lines. So again, you get the point where we end up with dw dz is going to be dx dz times partial w with respect to x plus partial y with respect to z times dw dy plus partial z with respect to z times dw dz, right? So awesome! We've got it now. These, let's box them all up, is how we're going to handle this, right? And again, this is the same answer you would get if you just brute force this thing and you made all of these substitutions into this function and then just took a bunch of partials. You would get the same thing. So here is chain rule for multiple input, multiple outputs. And you see the only difference now is we have to account for every pathway through the function of how a given input is going to make its way and affect all these other intermediate variables to affect an output, right? Okay, so now that we've got that, tell you what, give me a second and let's see if we can actually rewrite that boxed up equation in a little bit more interesting form. Okay, so now let's just rewrite these in matrix form, because if you notice, what, dw dx shows up here, here, here. dw dy shows up here, here, here. dw dz shows up here, here, here. Let's just pull those out. So that's all I've done right here. So I've just rewritten these in matrix form by pulling those out on the side, okay? Now what I'd like to do, tell you what, let's just transpose both sides. So I'm going to put a big parentheses around this, transpose it, put a giant parentheses around all of this stuff, transpose, and everyone remembers the rules with transposing, right? When you have the product of two matrices, you're going to transpose them. I got to flip the order and then transpose both. So this guy, instead of being a 3 by 1, turns into a 1 by 3, right? And it comes in the front. And same thing here, this 3 by 3, I just got to transpose the rows and columns, so I get this, right? Now, if you look at this long enough, does everyone remember, and actually maybe I'll flash this up here, our previous video where we talked about the Jacobian matrix, right? All the Jacobian matrix was doing was, that's exactly what the Jacobian matrix does. It calculates the sensitivities of a multi-input, multi-output function for all of the inputs and all of the outputs, right? So the Jacobian matrix, it's actually the way to capture all of these partial derivatives in a nice, clean fashion. So in other words, what I'm getting at is this term right here, this matrix here, right? This is, if you think about it, it is the sensitivity of the f function, right? It is how are these outputs of the f function related to inputs of the f function, right? What's the sensitivity, right? What are the slopes? This is the Jacobian matrix of the function f, right? And then this guy right here, this is nothing more than calculating how does x, y, and z vary as the inputs if you change r, theta, and z, right? That's this entire green box here, right? So this green box is basically, this matrix is the Jacobian matrix of the green box, right? So this is the Jacobian of G, right? So this is awesome. What we're getting at is the sensitivities or the slopes of the entire composite function. It's nothing more than the product of these two Jacobian matrices, right? So this is a way cleaner way to get at it. And it's basically capturing every single pathway of every single input variable to every single intermediate variable to every single output variable. It's all captured that way, right? So at the end of the day, we end up with the thing we're looking for, right? This term here, it's nothing more than the Jacobian of this f times the Jacobian of G. And again, got to be careful, right? This is a little interesting in terms of the order, right? These are all matrix operations, so you can't just flip-flop these in, arbitrarily. So it's actually, you work your way backwards, so you get Jacobian of F times Jacobian of G, right? And now, let's actually go ahead and extend this now to actually, this formulation is good for single input and single output, multi-input, single output, and multi-input, multi-output, right? This basically captures elegantly every single possibility. So, you know what? Let me erase this, and I want to, let's look at a quick example. Okay, so let's look at now a multi-input, multi-output function, and in fact, let's daisy chain even more together. So instead of just two sub-functions making up the composite function, let's say it's three of them here, right? A G, an F, and an E. So now, this Jacobian approach is going to be way easy. We're going to knock this out in like 30 seconds of what we just spent the past hour talking about. So here, you can see, okay, I can just focus on G. This Jacobian, right, it's just going to be all the partials of all of these outputs with respect to all these inputs. So this is going to be what? It's going to be a 2x3 matrix of partials, right? Then this one, this subfunction F, I can go stare at it by itself. I can go get its Jacobian, right? It's going to be a 4x2 matrix, right? And then lastly, this subfunction in orange, E, I can get its Jacobian matrix. It's going to be a 2x4 matrix, right? So now, what I really want, what chain rule is trying to get me, it's partial of all of the outputs with respect to all of the inputs, right? So again, we see this is going to be a, it's supposed to be a 2x4 matrix, right? Because there's two outputs, or sorry, it's a 2x3, excuse me, right? And three inputs, right? So the way I'm going to get this now is I'm just going to use our Jacobian matrix composition to get simultaneously do chain rule for every single path through this operation. So again, let's do it in reverse order. So I think this is going to now be, right, Jacobian of E multiplied Jacobian of F multiplied by Jacobian of G, right? And if we want to check ourselves, let's check dimensions, right? This is a, what we said, it's a 2x4. This one in the middle is a 4x2, and the one on this end is a 2x3. Yep, okay, so, yep, those check out, and we end up with, yep, we end up with the 2x3. So there you go, check this out. Three matrix products is basically chain rule in a general sense for an arbitrary number of subfunctions making up an arbitrarily complex composite function. So if you think about that, that is actually an incredibly powerful statement. We now have a matrix formulation of how to calculate partial derivatives or sensitivities for an arbitrarily complex function here, right? And we do that by basically looking at calculating derivatives or partial derivatives of each of these subsequent components. So this is literally like Lego building blocks, right? You take a Lego or a derivative of one little subfunction, you multiply or you combine it with another little subfunction, combine it with another one, and you get the overall derivative or the overall sensitivity of the overall function after you've combined all of these pieces together. So this is the building block of things like looking at neural networks or the backpropagation algorithm in neural networks. There's a ton of other applications of where you're going to see this chain rule pop up in a lot of different engineering applications. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed this video, and if so, I also hope you'll consider subscribing to this channel. Surprisingly, it really does help if you just click on that subscribe button or the like button or share this. It helps the channel grow and reach more people and help more engineering people around the world. So with that being said, I hope I'll catch you at a new one. Remember, the new videos come out every Monday, and I look forward to seeing you there, and hopefully we can all learn something new together. So until then, I think I'm going to sign off. Thanks. Bye.